Okay, thank you all for joining. Our next speaker is Anirudh Goyal. He's a PhD student at Mila, studying with Yashua Bengio. You wouldn't be able to guess from his publication list that he's still a PhD student. He's done a lot of great work on a variety of topics, from RNNs to reinforcement learning, and more recently he's been working on how to do sophisticated planning in an RL system and long-term credit assignment. And so he'll be talking today about modularity, attention, and generalization, efficient information dispatch in neural computations. I'll turn it over to Anirudh.
Thanks to Professor Roger Cross for the invitation, as well as thanks to Professor Sham for inviting me. Myself, Anirudh, I'm a PhD student with Joshua, and I'm going to talk today about modularity, attention, and generalization. This is joint work with my collaborators, as well as a great set of advisors. And just to begin with, or just to give an overall intuition about my talk, I'm going to talk mostly about dynamical systems. And to begin with, let's start with the simplest dynamical system. Let's say you have to model the motion of two bouncing digits, in this particular case 7 and 8. And a particular way to actually model the dynamics is, let's say you have a particular encoder which reads information from the pixel and converts into some high-level representation space. And you have some kind of a dynamics model like LSTMs or transformers, which learns the evolution function of the visual representation. And if you are constructing, then you have a decoder which takes the next step and converts it into image. Now, one interesting thing is, like, physical processes in the world often have a modular structure, with complexity emerging through the combination of simpler subsystems. And machine learning seeks to uncover and to use regularities in the physical world. Although these regularities manifest themselves as statistical dependencies, they are ultimately due to the dynamic processes governed by physics. For example, in the simpler bouncing MNIST task, we can model the motion of these two digits as separate independent mechanisms and only consider the interaction function when there's kind of a collision or overlap between these two digits. But on the other hand, if you see current dynamical systems like LSTMs as well as transformers, they generally put all of the information in the same computational stream. And I'm going to argue that putting all the information in a single computational stream can actually be a hindrance for catastrophic forgetting as well as robustness and generalization. So the outline of the talk would be, I'm first going to talk about the importance of factorization as well as knowledge decomposition for solving generalization as well as robustness problem. And then I'm going to talk about the implications of factorization for dynamical systems. And then I'm going to connect certain ideas, but I'm going to talk to programming languages as well as causal models, and everything to make sure that we have representations which can generalize to distribution, which we have not yet seen. To begin with, I'll first like to talk about a simple task which I really like. This is a very common Stroop effect from cognitive physiology or cognitive psychology. The task is, you don't have to read the words, you actually have to read the color of the word in which it is written. On the left panel, you can see both the word as well as the color of the word is exactly the same. On the other panel, it seems the opposite. And if you try to read it, you'll actually have to pay certain effort in order to actually read it effortlessly. On the other hand, like, we have been used to do reading operations mostly all the time. Like, we read without any stressing ourselves or without much thinking. And even in the simplest task, like even the simplest change, like I just changed the color of the words. And this effortlessly reading has converted to a task in which we have to actually spend some efforts, or spend some energy. What cognitive science tells us about this particular problem is that there are kind of two modes of decision making. One is automatic responses. Basically, your perceptual inputs directly trigger your actions. That is, you don't really have to do much thinking. And kind of there is some sort of a controlled behavior in which your automatic responses are overridden in order to better align your behavior with your goals as well as reward functions. Given a simpler example, let's say you're going back home from your lab to your home. And generally, if you're walking, you don't really need to think too much about which way to walk because you're being habitual of doing walking. But let's say you're especially in Montreal, there's a construction going on which is very frequent, then you have to spend some time thinking, okay, what's the efficient or what's the best way route back to your home? I'll come back to these insights a bit later in the talk. A big challenge in reinforcement learning, and AI more specifically, is to devise methods which have complex generalization. In machine learning, more specifically supervised learning, we have been able to solve single tasks, or we have been able to achieve pretty good generalization in some limited way. At the same time, we have been able to solve many complex tasks, but single task efficiently. For example, Montezuma's Revenge, AlphaGo, machine translation, as well as ImageNet. But what we essentially want is, we don't want a learner to solve only a particular fixed distribution. We essentially want it to solve or use the background information which has learned over the past knowledge to solve tasks, even an unknown task. For example, in like kind of a transfer learning setting or in kind of a continual learning setting. In a sense, we have been able to buy specialists which can solve a particular task. What we really want is kind of generalists, such that the ability to transfer knowledge to many tasks which are not even yet known to us as a learner. And in order to talk about such tasks, we first need to define what the data generating distribution is. For example, in this particular image, let's say this red blip is an agent, and this is just a navigation scenario modeled by many rooms as well as certain objects like keys, balls, and locks. And in this particular, given these particular knobs, you can define a task distribution which is diverse, that is, it consists of many and many tasks, is growing. You can define more tasks endlessly by changing the size of the rooms or by doing meaningful interventions on the underlying data generating distribution, as well as task distribution is compositional, that is, each task consists of 2 or more subtasks. In this particular setting, it's essential that your learning agent can generalize or as well as can transfer knowledge to a new task. Now, learning agents normally face non-stationarities. For example, in reinforcement learning, an agent is interacting with the environment, making certain actions, which it's releasing into the environment, and then there's an effect. Since the agent next state kind of directly depend on their actions, then it's important to think about these non-stationarities. As well as there are other agents in the environment, and because of their actions, the environment can also be changing. So there can be stationarities because of their own actions as well as because of the actions of other agents, which is again a field in machine learning, for example, multi-agent reinforcement learning, which is also very popular these days. Now, interesting thing to think about these changes is, as an agent, if I'm interacting with the environment, there are not many entities or there are not many objects in the environment which are relevant to me. For example, a learning agent that need not devote equal attention to all the subsystems at all the times. If I'm an agent, if I'm interacting with the environment, there are only certain aspects that significantly I need to interact with as well as need to consider in order to come up with a plan or in order to take a particular action. Now, there are certain ideas from causal learning community, essentially of independent mechanisms, and the notion of independent or autonomous mechanisms has been influential in the field of causal inference, where it is applied not only to dynamic processes, but also to kind of independent datasets. A complex generative model, temporal or not, can be thought as a composition of independent mechanisms or causal modules. In the causal community, this is often considered a prerequisite of being able to perform localized interventions upon variables determined by such models. It has been argued that the individual modules tend to remain robust or invariant, even as other modules may actually change. And one may hypothesize that if the brain has to solve multiple problems beyond a single IIT task, it would be economical to learn structures aligned with this by learning independent mechanisms that can flexibly be reused, recomposed, and repurposed. The key takeaway here is that it's important that the interventions are localized. What it really means is, like, if I'm as an agent, I'm interacting with the world. If I interact a particular agent, it doesn't change the entire environment around me. So an intervention by myself or by other agents in the environment, it only changes a particular aspects of the environment. That is, the change is sparse over time. An interesting question here to think about is, how can we discover these mechanisms? That is, how can we factorize knowledge in a way which can result in a representation such that any semantic intervention or any diagnostic intervention in that representation space results in only sparse changes. Okay, for example, let's say you have these blue pips, which are just the decomposition of the knowledge, and any structure over them means like how it is kind of connected with the other function or other node. And let's say we make a particular intervention. Intervention is seen by the red color. And after changing the intervention, I only need to change the immediate variance, immediate effects. I don't need to change the entire graph. So essentially the goal is, while we're learning representations, we want to learn such a representations where change can be localized. And this change can be due to our own interventions, as well as because of some other uncontrollable change, which we can't control. Now, in order to motivate us, I'm going to talk about the simplest example which we can think of and say that why such a knowledge factorization is important, and if we have an incorrect factorization, how it can lead to poor transfer. Consider two random variables, a and b, with a cause of b. Now, let's say the correct causal model decomposes as marginal of a as well as conditional distribution of b given a. Now, you consider two distributions, p1 and p2, where you intervene on a, that is the marginal of a changes, and we can obtain many distributions like p1 and p2. Now, consider another distribution where you have the wrong factorization, that is marginal of b as well as conditional of a given b. Now, in these two distributions, if we intervene on the marginal of a, it actually influences all the modules because marginal of b has also changed as well as conditional of a given b has also changed. In the right factorization, when we intervened on a, it only changes the marginal of a. It didn't really had any effect on the condition of b given a. So as you can see that even in the simplest example, this is kind of a very standard situation with standard neural networks where you have a one big monolithic network, and this entire monolithic network is trained by gradient descent, and every parameter participates to every relationship between all the variables. Basically, it's an entire monolithic network. So the one hypothesis is, like, because of the gradient descent and because the entire weights are affected, all the weights are kind of co-adapting with each other. Hence, when there's a change in distribution, all the weights kind of adapts, and which can lead to poor transfer. On the other hand, if we have a good decomposition, it can be useful because when there's a change in distribution, we don't need to adapt the entire network. We only need to adapt a change which needs to be changed. But the interesting question to think about is, how can we learn such a factorization? There has been a branch of research mostly led by Professor Josh Tommenbaum's lab and his collaborators, where they also connect the notion from causal networks as well as probabilistic programs. For example, object space forces and time mechanisms. And I think this is very interesting. One interesting drawback or limitation or something to think about is these particular networks, what they already assumed is essentially that the representation of the variables for these networks or for learning these Bayesian graphs are actually given, and you're just learning the topology of the graph. The problem for deep learning is how to come up with the representation or the right representation space in the first place. And there are certain ideas definitely from probabilistic programming, which I think are very interesting for learning invariant representations. Again, coming back to my example, if you have a normal canonical systems, let's say LSTMs and transformers, they are going to put all the information in the same computational stream. And if there's only a slight change in the parameters as well as the distribution, the input distribution, it's going to affect the entire network, basically the LSTM, basically our dynamical system. And hence, when there's change in distribution, if you're not given enough data, it may lead to poor transfer. But one natural way to model this particular distribution, it would be, let's say you have two independent as well as different dynamical processes, one for each digit, and you're only considering, and they're operating by default, and you're only considering the interaction function between these independent processes. And the word of the use independent just means like information about the one mechanism doesn't tell you anything about the other. Right now, I'm kind of loosely using the word mechanism. Further in the talk, I'm going to delve into what's the formal definition, or what's the formal way to talk about these mechanisms, the way we use it in our paper, in our work. As I said before, that if we have a way to learn modular representations, it could have better transfer as well as continued learning, because there must be some information which could be shared between a new task as well as the previous knowledge. It also makes easy for the model to keep these two processes separate, which could also have long-term information storage. For example, there's an event which happened right now, and then there are lots of time steps in which there's only kind of a distractor information or noise information, and you want to remember or as well as recall the event which happened many time steps back. And there's problem while training dynamical systems, which is called as like normal vanishing gradients as well as exploding gradients. Even in transformers, the sequence of length could be an issue. So such a decomposition of knowledge can also make long-term grade assignment much easier. Now, what I'm going to say is, in the left figure, this is a normal RNN or normal LSTM, where the input is coming at each time step, and you have the hidden states at each time step. And what the way I'm thinking is, in the dynamical system, we can think of an overall system being a state as a composition of number of fairly independent subsystems that evolve over time, kind of responding to forces and interventions. A learning agent that need not devote equal attention to all the subsystem at all times. Only those aspects that significantly interact need to be considered jointly while taking a decision or forming a plan. Now, such sparse interactions can reduce the difficulty of learning, since only few interactions need to be considered at a time, reducing unnecessary inference when a subsystem is adapted. Such models of the world can also better generalize across tasks where only a small subset of mechanisms or processes needs to be changed, while most of them remain invariant. The central question motivating our work is how a machine learning approach can learn these independent but sparsely interacting recurrent mechanisms in order to benefit from such modularity. So idea is, what we are just going to do is, we are going to assume that there are many independent dynamical systems, and depending upon the contextual information, they decide dynamically to which particular other module as well as which other particular mechanism they share information with. And the way I use mechanisms is just kind of a transition operator. They take particular information, they take the state of hidden state at times of t, they take the contextual information, it could be the input, it could be the language information, it could be anything else, for example goals, and it predicts the next state, for example ht plus 1. And you evolve this function over time such that it has a notion of memory, for example LSTM. Now till yet, I've only talked about the basic picture of how such a model can benefit from modularity. Now I'm going to talk about what are the Desertrata, which I think is essential for learning such model, which could lead us to better transfer as well as better generalization. So before saying, till now I've laid out a for case for building models composed of modules which by default operate independently and can interact in a limited manner. Accordingly to our approach, to modeling the dynamics starts by dividing the overall model into small subsystems. Our model encourages sparse interactions. That is, we want most of the modules to operate independently and follow the default dynamics most of the time and only rarely sharing information. And right now I'm going to talk about what are the Desertrata for these modules to capture modular dynamics with sparse interaction. For example, let's talk about another example. Suppose we are looking for a particular object in a large scene using some kind of a limited processing capacity. One way to say is like our capacity of parallel processing and as of reasoning with high-level concepts is limited, and many brain systems representing visual information use some sort of a computation to allocate resources. Now, competitive interactions among multiple objects, unless they are present in the visual information, they can operate automatically as well as operate in parallel across the visual field. Interesting part is there's a kind of a top-down bias originating from the higher areas that may enable us to devote resources to input information that may be of particular interest or relevance. What essentially it means is, let's say each of these modules have a particular belief, and only module attends information to that particular object which is relevant to its own belief. Second, capacity. There is a trend in machine learning or deep learning specifically is to learn one big model for everything. And as I've said, like if you have one big model for everything, one problem which arises or which could arise is of like not having a proper transfer. And what we are thinking is if we have an ensemble of such modules such that we constrain the capacity of each of the modules such that by definition, a particular module can't represent the entire world around itself, but as an ensemble of these modules, the kind of complexity emerges as a combinations of these simpler subsystems. We also want diversity, that is, different modules should capture different aspects of the world, but as a collection, they should be able to represent the entire world. We also need to think about kind of a communication channel. For example, if different modules are focusing on different aspects of the world, then in order to take an action, in order to form a plan, they still need to think about how to efficiently share information with other modules, with other aspects of the environment, and all this to make sure that such an ensemble of modules can systematically generalize to other tasks as well as to new distribution. For example, let's say you're crossing a street. By crossing a street, generally you don't need to pay attention to the positions or to basically the colors of the car or as well as type of the car. What you really need to pay attention is to positions as well as velocities of the car, kind of disregarding their color as well as their type. This kind of information bottleneck or this kind of some sort of an attention seeking has been shown to improve generalization in deep learning as well as machine learning. Inspired by this, what we are going to do is we are going to apply some sort of a competition between different modules such that different modules only get information according to their own beliefs. In this particular example, let's say you have a visual input, and let's say there are three different objects, a triangle, a square, and pentagon. You run some sort of a visual encoder on top of this to get a representation of this particular information. And these boxes only says you have four different modules, different in the sense they have different parameters and they have their own beliefs. In this particular case, their belief can be as a function of their hidden states at past time steps. And each module only gets information which is relevant to their belief or which matches their belief. And such a top-down filter not only enhances the target, but it also suppresses other stimuli, including the distractors. And what we employ is, we employ a competition between the different modules such that different modules can attend to relevant parts or distinct parts of the visual information. It means, let's say if you have an ensemble of 10 modules, in this particular case 4, we allow only top 2 of them to be activated, and rest just follow the default dynamics.
Okay, so looks like we have a question. So in this proposed framework, so a question from the audience. So in this proposed framework, you would still have to think about having the modules learn compatible features, or would you sidestep that using the communication protocol?
I think you're right that if different modules have different dynamics, you still need to learn about a way to essentially the different modules still speak the same language. And I'm going to talk about how I sidestep the problem that they don't speak different languages. The idea is basically using some sort of an information form, some sort of attention. So yes, we have to think about how they learn compatible features. Should I start?
Okay.
Okay. So till now, I've again said like we want certain functions such that it only attends to type of information which they found in the visual field. And if the type of the information doesn't match, then that particular function, that particular module doesn't get activated. When we are thinking about it, something which arises is the notion of typed argument functions, which are popular in like kind of a traditional programming languages, like for example, C. What typed argument function means is, let's say you have a function has a particular type, let's say int, string, or float. A function has particular arguments or types. These could be like type of the variables which this function operates on. So one intuition is having such functions which have types as well as the variable have also types is kind of an interesting way to look at it, because this function can operate on any variables as long as the type of the variables matches the type of the input the function expects. For example, if let's say take a simplest example, add. If you have a function which just add two integers, no matter what you have learned on, like it can add 1 and 2 as well as 1 million and 3 million. It doesn't care about in distribution or out distribution, just because the type of the input matches to type of the input this function expects. So we are going to use similar intuition, and the notion is we want each of these modules to reflect or to learn representations or to learn a function f such that the query is dependent on f, and the types, which can be the information coming from the other modules as well as the information coming from the visual or from the external environment. That particular function knows what kind of information it wants to process on and what kind of information it wants to throw off. One way to dynamically combine information in machine learning, which has been very useful, is the notion of attention. Attention can be thought of as dynamically creating kind of a dynamic connections as compared to normal like neural networks in which the topology is fixed. And specifically one form of content-based attention which has been very influential is something called key value attention. And just to summarize, let's say you have particular input X. What you do is you compute like linear projections, which are called query keys and values. And depending upon a match between keys as well as queries, you send information based on the values. One way to think about this is, let's say I have a particular question in deep learning, and let's say my query contains information about deep learning. And let's say I asked to Yasha, and Yasha has competence in deep learning. So his key contains like his key tells something that he's competent in deep learning, and the value could contain answer to my question. What people in transformers do is they stack these functions, or they use these, which they call head, such that each head has different set of parameters which compute different queries, different keys, and different values, and they operate on this set of tensors as compared to normal tensor. Again, what we want to move is we want to move from attention to indirection, which means is for a particular module computes some particular query. Keys and values can come from other modules as well as information from the environment. And queries contains some sort of like what kind of information I want. And if there's a match between queries as well as keys, you get an answer or you get information in terms of values. Now, the notion of indirection is important because it doesn't matter where the information is coming from. It could be coming from, like, a module 1 can get information from module 3 as well as module 5, as long as it just has the right information. In a sense, what it buys us, it buys like each module can independently decide what kind of information it wants to act on. So it also provides a way to better decide generalization as well as efficient rate assignment. One interesting thing about all this is, like, because of this multi-head key value attention, each layer can be interpreted as a set of vector valued elements. What each level does is it transforms a particular set into a new set by applying the same function in potentially different ways to different subset of the arguments. And each of these functions operates on only one element, and it can take other functions as arguments, again soft picked by attention. I'm going to decipher, I'm going to say a bit more about this particular slide. What I meant is, let's say each module is representing a function. Now, that particular module have a belief, which is basically a query, which is again the function of its hidden state, and outside information, basically the keys, are coming from other modules as well as the information. And if the query by a particular module matches the keys to the other information, then there's a match. And this mechanism would look at kind of the input object's keys and evaluate if its type matches with what a particular module expects. And if there's a binding, then this module computes that particular function. In a way, here each function or each module itself is deciding what kind of input it wants to operate on. The only crux is that that particular input, the type of that input, should match the type of the input the function expects. So till now, I've summarized, I've kind of given basically some sort of a summary of what kind of model we want. We want, like, you have a dynamical system, and you can think of overall system as being composed of a number of fairly independent subsystems. Each of these subsystems have particular beliefs, and they only operate if the belief in the environment, or if the information in the environment matches to their belief. If there's a match, then the mechanisms which actually win the competition, they can communicate information with other mechanisms, because, you know, if there are many objects and different modules are attending to different objects, in order to solve the task, you kind of still need to communicate information. And the inactive mechanisms, the mechanisms which didn't win the competition, they follow the default dynamics, in a sense that they may have information from the past which may be relevant for the future, and hence they don't do anything. They don't interact with the mechanisms. Coming back to my Stroop task, the notion of default would be the reading. Like, we are habitual of reading something on the right panel, and the notion of relevant information or active mechanisms would be, let's say, one, you have the color module, which is saying, okay, what the color of this particular information should be. Another is reading, and you have to combine put these two together in a dynamic way to actually say, to solve this particular task. Just to give you an overall detail of what a particular architecture looks like, is all these boxes are basically different dynamical systems which have different parameters. You have particular external input, which is coming at time step t. Each of these dynamics model are operating by default. That is, they don't share information at the first time step with anyone. But depending upon the input, there may be information in the input such that a module says that, okay, there's a particular object present in the input, and I know how to operate on it, such that the mechanisms which are win the competition, they get to read information from all the other modules. So there's a communication step which shares information between different modules, but this communication step is sparse in a way that we only say the relevant mechanisms, or the mechanisms which win the competition, they should be able to read information from other mechanisms, because other mechanisms may contain information from the past which may be relevant for the future. So there are 3 steps. One, first you have to decide which are the mechanisms which win the competition, or which are the dynamical processes which are win the competition, which is input dependent. Then there's default dynamics, and then there's a communication step. The mechanisms which win the competition, they share information with each other. I'm going to go through the 3 steps. The first one again is like top-down modulation, basically the selective activation of RIMs. What essentially it is, let's say you have particular visual information. It could be visual information, for example, output of coordinate. It could also, for NLP problems, it could just be like word embeddings and stuff, output of the word embedding and stuff. I concatenate the null information with it. And what now happens is each particular module emits a particular query, which is a function of hidden states, as well as the keys and values are a function of output of, like in case of coordinates, a perception model. Now we decide a match between the queries, which are just a function of hidden state, as well as keys. Now, depending upon this match, only the top k modules, which have the highest match, they get activated. The modules which have the lowest score, that is, their beliefs doesn't match to anything present in the input, they follow the default dynamics. By default, I just meant like they copy their past state. Similarly, now once you have decided what are the mechanisms which have won the competition, the next step is to think about how to actually share information with each other. Think of it like that, like for example, you have a particular team, or you are doing a particular project on, let's say, variational information bottleneck or quantum science. You need certain people. You need someone who have ideas about variational information, as well as variational inference, as well as information bottleneck, as well as know something about quantum science. And different members of the team have their own competence, as well as here also like different mechanisms have their own competence, their own beliefs. They know what kind of objects they want to iterate on. But in order to solve the problem at hand, they need to share information. Here again, what's going to happen? A mechanism which won the competition is going to read information from all the other mechanisms. What it means is a mechanism which has won the competition is going to emit a query. Again, this query is a function of hidden states. The keys and values is going to come from other mechanisms. And depending upon this queries, keys, and values, the information gets transmitted to a particular mechanism which has won the competition. And this communication sharing is just because of through a bottleneck, so that you only transmit the information which is necessary, not you transmit all the information. So there's a compression step involved. That is, you don't transmit all the information. You only want the agents. You only want different modules to transmit information, which is very necessary. Just to give a very intuitive example or very illustrative example, let's say you have 3 mechanisms, and let's say xt is a visual input. We append null to it, and now use an attention mechanism to select the active RIMs or active modules based on the magnitude of their attention weights. Now let's say H1 as well as H3, the ones which are shown in red, they get activated. H2 is not activated because its belief doesn't really match to what the information present in the input. This module just follows its default dynamics, that is, it just copy the hidden state. And the one which is activated, HT3, it share information from H1 as well as H2. Why H2? Because this one could contain information from the past which may be relevant for H3, but it doesn't send gradients back to H2. It only propagates gradients through the active mechanisms. It doesn't propagate gradients through inactive ones. So that's the basic idea behind the architecture or behind the intuition. that what you want is you want an ensemble or you want a system which is composed of a number of fairly independent subsystems that are evolving over time, responding to forces and interventions. Depending upon the visual information, we first decide which of the ones are relevant. The relevant mechanisms, they share information with all the other ones, and the inactive mechanisms, they just follow the default dynamics, which for us is just copy the hidden states. And right now, I'm going to talk about certain diagnostic interventions for certain kind of problems, which we did in order to say that why such a model is interesting. And the main goal of our experiments is to actually show the use of such models improve generalization across changing environments in kind of modular task and to explore how it does. Our goal is not to actually perform highly optimized baselines, but to study kind of the the diversity of our approach by applying it in a kind of a range of diverse tasks, focuses on tasks by changing an environment. And since in our proposal, the idea is like each module has a particular belief and it only attends information if the information matches to the belief, then such a model should be more robust to any kind of distractors present in the input information. Again, in an video's sign of scenarios, for example, my bouncing digit task, it could learn different modules can learn representations which are better aligned to different objects, as well as for visual Atari-based games, for example, in Atari, as well as reinforcement learning tasks, will show that different modules can actually be responsible for certain events as well as object-based representation. First, we kind of turn our
questions. When you talk about belief, are you using this in the Bayesian sense?
Yeah, so what we want is like, I'm not using it in a Bayesian sense. This belief is just a function of the hidden state, directly the hidden state. So it's a deterministic mapping. My intuition was to just say that this deterministic mapping is acting as a belief for a particular module.
So the follow-up is, so it's more like attention?
Yes.
Okay.
But the attention is driven by the state of a particular module. So if I'm a particular module, I only get information which is relevant to me. Like if I'm only attending to a particular shape, let's say a triangle, I don't want any other information from the visual scene. So kind of a top-down attention.
Okay.
So first we turn our attention to the task of receiving a short sequence of characters, basically a copying task. The task is you have some information for the first 10 bits, and then you have a distractor phase. There are lots of zeros, and you have to kind of reciprocate information from after this distractor phase, and you have to copy the information from 0 to 10 time steps. And what the intuition is to show that there are a particular set of RIMs, or there's a particular set of modules which can attend information in the input phase, and the modules during this distractor phase can remain dormant. And again, when you are supposed to produce information from the input, you can just reciprocate. So it's more of a memorization task, but the idea is there are two phases in the task. One is kind of an information seeking, in which you have to see what's the right representation or what's the right information. Then there's a distractor phase, in which the representation, you have to just stay dormant. And third phase, you have to again reproduce the same information as you have seen in the 0 to 10 time steps. What we essentially do is we train certain modules like our proposed model, as well as LSTMs, as well as transformers, on a sequence length of 50, and we test on larger sequence length. In the figure, it just shows result for 200, but it's valid for even longer subsequences. And just the idea is, can we see that certain RIMs can specialize over the patterns? And if you see the figure, it shows you the activation pattern of a particular module. The black means that the particular module remains dormant, and white means that the particular module was active. And if you see in this particular figure, it kind of shows clearly that the modules which were active in the first 10 time steps, they were more dominant in middle in the distractor phase, and then they again started producing information after the 50 time steps. Similarly, in the line of a similar task, we are motivated by the intuition that the different modules kind of activate only on the relevant part of the sequence. In order to show that, what we did was we trained a certain model on like some kind of an MNIST or some sort of a CFAR, and we trained on like lower resolutions, and we test on some higher resolution. And one interesting thing to think of is, can we learn? It's kind of a like classification task. You have to read the pixels, you have to read the MNIST digit pixel by pixel and row by row in a kind of a raster scan. And at the end of reading, you have to tell like what kind of sequence it belongs to or what kind of class it belongs to. So it's a classification task. And we see that on CFAR, what really happens is there's a particular module which is responsible or which learns to attend to the foreground and totally ignore the background. In this example, I just show a activation of one particular module that when it's activated, and you can see that the activation of this particular module is strongly correlated with the foreground pixels. We also test this particular thing on MNIST. What we do is we train on smaller resolutions, like 16 cross 16, and we test on like higher resolutions, like 19 cross 19, as well as 24 cross 24. Now, the idea for testing is basically simple, that the design is motivated by the hypothesis that the generalization performance can be improved by having modules which only remain active on the relevant parts of the sequence. And since MNIST resolution only contains like black and white pixels, so if you increase the resolution, you should be able to ignore the background information and hence show better generalization as well as transfer. Again, we compare to all the other baselines, for example, LSTMs as well as transformers. And we see like for even a simpler task, such a model kind of outperforms a fairly basic number of baselines. Again, the idea was not to study like or to outperform baselines, just to influence or just to show the effect that if you're constructing certain inductive biases, your model can actually learn which of the modules should remain activated, and it can learn representations in a way which compartmentalized knowledge. In this particular case, you just want a foreground as well as background separation. Again, so we have kind of presented evidence that such a system where you are actually presenting over, like thinking over different modules, can generalize over temporal patterns. I now turn our attention to show that different modules can actually specialize to different objects and show how improved generalization to settings where we add or remove multiple objects at a test time. We consider a very synthetic bouncing ball task in which multiple balls of different masses and sizes move using basic like Newtonian physics. What makes this task particularly suited for proposed model is that the balls actually move independently most of the time, except when they collide. And during training, the objective is we need to read the pixel level information and we predict the next frame at each time step using like normal teacher forcing or using like normal RNN training. And then we use this particular model to generate kind of multi-object rollouts. As a preliminary step, what we did is we tested both the baselines as well as our model, and we tried to roll out for 15 time steps. And as you can see that there are different data sets. One was just like normal 4 objects in which there are 4 bouncing balls are present. Other one was like 6 to 8 objects in which there are like more number of balls. We increased the more number of balls. And one particular task was also curtain, in which we introduced an invisible curtain such that the different modules, different models have to remember like how to remember the trajectory of the ball through that invisible curtain. And essentially what we did here was we trained something on 4 objects. That is, we trained an ensemble of frames on 4 objects, and we at test time we added more number of objects, like we added 6 to 8 objects. Each training sample has different numbers. It could be 6, it could be 7, it could be 8. and we test the generalization performance with compared to like normal LSTMs. And we see that for both the trained on 4 objects and testing on 6 to 8 objects, as well as trained on 6 to 8 objects and tested on 4 objects, we achieve better performance in terms of like cross entropy loss over the generated sequence. Again, one thing as I mentioned was like better robustness to distractors. So we again consider some kind of an object picking reinforcement learning environment in which an agent must retrieve a specific object during the presence of distractors. We kind of use a partially observed formulation of the task where the agent only sees a small number of squares ahead. And these tasks are normally difficult for an agent to solve because the sparsity of the reward, as well as because the agent receives reward only after reaching the goal. And what we really do is during test time, we add more number of distractors as to what we have seen during training. And if you added distractors, it actually interferes with the representation which your like perception module, in this particular case, a CNN is learning, as compared to if you have in a case of a top-down attention, which each module have a belief and they want to only attend to a specific information. Because if you have a particular partial view, you have already filtered out much of the information. So if you have another inductive bias which forces you to look for specific objects, that might also help you to distract us. So it's a simple imitation learning task. There's no reinforcement learning. And so it's basically like kind of like normal supervised learning. At each step, you know what the optimal action is, and you're just supposed to like regress to that particular action. As you can see, like even the training task contains like distractors, and the particular LSTM baseline in this particular case fails to solve the task perfectly. And during test time, when we add even novel distractors, you can see when the performance of our baseline actually falls drastically from like 100% to 40%, but the fall is even worse for LSTM. So this also provides certain evidence that in terms of while introducing novel or new distractors, not the entire model changes. Now, as a last experiment, which I find something very interesting, we investigated how UTRMs use specialization in order to improve generalization to changing environment, basically a factors of variation of data. And I think there's a kind of an intriguing connections between the different modules in our proposed model and the concept of affordances from cognitive psychology. Now, to perform well in environments with a dynamic combination of risks and opportunities, an agent should be ready to adapt immediately, releasing into execution actions which are kind of least partially prepared. This suggests that agent should process information in a contextual manner, building representations of games or potential actions that the environment currently affords. In a sense that there's a word from cognitive psychology called affordances, and a particular object can have different affordances. And one possible way to learn is that the agent should learn behavior in a way which reflects the potential actions which environment affords. In order to test this hypothesis, we actually ran our proposed model on the entire suite of Atari games, like 40, 45, like 48, 52 games or something. And what we did is we just replaced the underlying dynamics model, which is LSTM, with the proposed model, which is like kind of an ensemble of dynamics, which we call RIMs. And we just show how well or how bad the performance is. And we see for approximately all the tasks except 7 or 8 games, just having a drop-in replacement, like no hyperparameter tuning, kind of achieves a better performance. And the hypothesis was, like on further diagnostic interventions, we saw was like each module was learning a particular kind of an object-based as well as an event-based representation. Just to basically surprise, what we're essentially doing is like we want to modularize the decomposition of knowledge, we want to modularize the information present in the visual information into different modules, such that each of these different modules can dynamically decide from where they want information to, that from which particular module they want information to, or what kind of aspect of the input they want information to. In a sense, the computation in such modules is sparse as well as modular. The computation is also dynamic rather than static, because dynamic just because of attention. At a particular time step, we only select relevant modules or relevant mechanisms. And inputs and outputs of these model are actually operating not on fixed size vectors, but actually tensors or set of tensors. So which relates normally to the ideas from like programming languages and the idea of like argument functions or typed argument functions, which is also, I believe, a useful inductive bias for models to have, because they can also lead to better generalization as well as better transfer as well as better credit assignment. Now, someone might ask that, there's a term called independent representations or disentanglement, in which what we want, like the representation of a scene to be independent, for example, in VAs. And I think like the way I think is something different. For example, if you are given a representation of environment, the high-level objects, in this particular case, this table and chair, are actually would be correlated and hence would be independent. But I think what's more important or what's more interesting to think about is the independence of the mechanisms which are generating the data. Since input to that mechanisms are correlated, the outputs of these mechanisms would also be correlated, but the mechanisms which are generating the data, they are independent. And I think that's probably a better way to think about, or that's probably some way to think about as compared to thinking about disentanglement, where you assume some sort of an independence assumption in the high-level variables, which is completely opposite to what we imagine, because high-level variables are actually correlated. So we are exploring connections, how we can resolve this ambiguity. Another thing which we are thinking about is like...
Pretty soon, we're down to just 4 minutes.
Yeah, I would be done in 1 minute. So another thing which we have been thinking about is, in machine learning community, we have been thinking about building one big model for everything. And by now, hopefully I should have convinced you that it's important to think about how would we decompose knowledge, or how would we modularize knowledge. And one interesting thing to think about is, like, instead of building a one big model for everything, we only want to consider like partial word models, such that an ensemble in each of these word models only learn something which is relevant with their biases as well as their beliefs. And such a model could also be useful for planning problems, because you don't need to explore, or you don't need to search in the entire space. You only need to search in the space of these submodules. So these are mostly the references which I talked about, and most of them are on arXiv. So feel free to take a look at them. And if you have any questions, please feel free to ask me.
Okay, so the first question from the audience is, which were the 8 games you mentioned?
I don't remember, but I can see them. It was Atlantis, Frostbite, Venture, Trull, Crazy Climber. Yeah, all this information is given in the paper also on arXiv.
Okay. Is there anything special about those games?
Yeah, so what we did was, when I visualized those games, there were more number of objects as well as more number of events which are present. Like, there were certain enemies and there were many enemies. And after we saw that there's a performance gap, what we did was we just changed a particular hyperparameter. We just increased the number of modules, and we saw that after just increasing the number of modules, we were able to improve the performance on the 8 games on which we saw that our performance is not that good. So it was mostly a hyperparameter issue, because we ran the same hyperparameter on all the games.
Okay. Does anyone else have a question? give people a couple more minutes to respond.
I might say something then. So one interesting connection is to something called like society of mind. Essentially what we want is like different modules to represent different beliefs. Right. So Professor Sanjeev has questioned how efficient is implementation. Answer is my implementation is not efficient at all, partly because we use like NVIDIA kernels and I didn't wrote my own kernel. But actually, implementation-wise, if you are seeing a weight matrix, we actually have a block diagonal weight matrix. So it's much sparse as compared to normal one. So it could be much more faster, but right now my implementation is approximately the same time as LSTM. But that's just an implementation issue.
Okay, I guess that's it. So, so thank you for the great talk, and thank you to the audience for joining.
I also want to thank the audience as well as Professor Sanjeev as well as Professor Roger Cross for having me. Thanks and have a nice day.